All right, moving right along, we are going to, in this video, talk about integration by parts, which is another advanced method of integration. When I say another, I mean in addition to U substitution that we learned in the previous section, the last couple of videos. The idea with integration by parts is it'll help you answer questions like this. So again, we're figuring out antiderivatives. It's just another formula for antiderivatives. And the importance of antiderivatives, again, stems from the fact that we really want to be able to answer this area question, as you'll see later on in this class. There's lots of different applications of the definite integral. But the evaluation theorem told us that we can evaluate definite integrals if we can just figure out antiderivatives. So much of this class comes down to we just need to figure out antiderivatives. And while U substitutions are really powerful, they won't always work to figure out antiderivatives. For example, here's a question where you're being asked to find the antiderivative of x times e to the x that I don't think we could figure out using U substitution. And I also don't think we can figure it out using any of the more basic methods that we learned earlier on in this class. This doesn't look like too bad of a problem, but none of the tools that we have will allow us to figure out the antiderivative of x times e to the x. But by the end of this section, using integration by parts, you'll be able to answer this question as well as many others. So without further ado, if you look at this, you might notice that we have a product of two things, right? X times e to the x. You saw a lot of this in Math 251. In Math 251, the way you'd solve a similar question where you were asked for the derivative as opposed to the antiderivative is applying the product rule. And the product rule, most students just have memorized, oh, that's the f prime g plus g prime f thing. A little bit more formally, what it says, if you're taking the derivative of a product of two different functions, then that answer will be equal to the sum of two different things. So we're going to add up two different things. And those things individually are the derivative of the first function times the second function, and the derivative of the second function times the first function. So this is your Math 251 product rule, the f prime g plus g prime f thing that I bet everybody had memorized and used a whole bunch in Math 251. My first comment is it's not the least bit useful to answer this question because it tells you how to take the derivative of a product of two functions, and you're not asked for the derivative of a product of two functions, you're asked for the antiderivative of a product of two functions. So why did I write it over here? Well, somewhat surprisingly, we can manipulate this thing to come up with a new rule. That new rule will be our integration by parts formula, and that new rule will work on this problem. Don't believe me? Let me show you. So first off, we want to change this product rule into Math 252 notation. And what I mean by Math 252 notation is instead of derivatives, we want to talk about antiderivatives. Here's the product rule written in Math 252 notation. What it says is if the derivative of the thing on the left is equal to the thing on the right, then by our definition of what the antiderivative means, the antiderivative of the thing on the right is exactly the thing on the left. First observation, this is not the least bit helpful to answer this question that was asked. But have faith, we'll get there. What this is telling you is if you were ever lucky enough to be asked the antiderivative of something that exactly fit this form, if instead of asking you this example over here, I asked you this example, and you were kind of clever and noticed, hey, wait a minute, the derivative of x to the 10th is 10x to the 9th, and the derivative of sine of x is cosine of x, and these just happen to be written in the exact same order that my product rule is defined in over here. If somebody asked you this question, you could answer this question using the product rule written in Math 252 notation. You could say the antiderivative of this mess is exactly x to the 10th times sine of x. Why? Because the derivative of x to the 10th times sine of x is all this stuff. I guess you could argue that I should tack on a plus c here. Not really something I want to worry about at the moment. Anyways, if you were lucky enough to get this question, you could answer it. But let's be real. How likely is it that you're going to get this question, right? Doesn't this seem extremely contrived? Doesn't this seem like something that would never really show up in a question, that would not even be worth our time to memorize a formula to try to recognize this form? And that's all completely true. You are not going to memorize this as a new version of the product rule because this is a question is just too unlikely to ever see. What we're instead going to do is take advantage of the properties of the indefinite integral to rewrite this equation to get it into a form that'll be really useful. And that useful form will end up being the integration by parts formula. And the way we can do that is note that you are being asked for the indefinite integral of a sum of two things. And when we first started talking about antiderivatives, indefinite integrals, we learned that the integral of a sum is the exact same as the sum of the two different integrals. In other words, this line right here implies this line right here. The integral of this sum is the same as the sum of the two different integrals. Informally speaking, I can take this integral symbol and distribute it to each of my two terms. That gets me here. Okay, I don't see how that helps. This is if I were asked two different questions and what their sum was. Yeah, this form, we're still not done. But what we can do now is subtract this term from both sides of the equation. And this line here will end up being really useful. It might not look useful and it might seem like it'll be impossible for you to memorize, but it turns out that this line right here will end up being our integration by parts form. There's a lot of symbols and this doesn't seem like something I want to memorize, so let me write an easier version of this formula. The way I'm going to write an easier version of this formula is taking advantage of what we learned in the previous section. Use substitutions, right? This is really ugly looking, but I can make it prettier if I substitute some stuff. Let's let u represent this function g of x, and we'll let v represent this function f of x up in this notation. If u is g of x, then the derivative of u, du over dx, would be g prime of x. Another way I can write that is du equals g prime of x dx. Similarly, if v is f of x, then dv equals f prime of x dx. And I feel like I'm probably getting to the limit of your attention for following me derive this formula, but let me just point out here that if we allow these four substitutions, this formula is going to simplify dramatically because we have an f prime of x dx, which I can change into dv. We have a g of x, which I can change into u. We have an f of x, which I can change into v. We have a g prime of x dx, which I can change into du. And then we have this f of x and this g of x, which I can change into v and u respectively. What I'm saying is that these substitutions imply this formula. And to maybe emphasize the importance of this formula, I'm going to put a big box around it because this is our integration by parts formula. This is something that you will memorize, that every Calc 2 student who has ever taken Calc 2 memorizes. The integral of u dv equals uv minus the integral of v du. And you're like, how am I ever going to remember all the u's and all the different v's? I don't know, but everybody does, right? I do. I have to say the entire formula. Like I can't just write down part of it. I just have memorized in my head. The integral of u dv equals uv minus the integral of v du. u dv, uv, v du. You say it a bunch of different times. It becomes almost like a song. You don't mean to memorize it, but you accidentally memorize it. You will want this formula memorized. This will be your integration by parts formula. You don't really need to know the whole derivation for this. I just think it's kind of interesting, and I think it's kind of cool how we used a u substitution to change this ugly form into this form. But really, the end product is all that you need here. The integral of u dv equals uv minus the integral of v du. Right? Maybe you could see all the different parts in blue that corresponded to these parts in green. The great thing about this formula, it tells you the antiderivative of a product of two things. The bad thing about this formula is it doesn't give you the answer. It gives you an expression that represents the answer, and inside that expression is another integral. So it's not a one step and you're done kind of situation. It's a let's change this question into this question, where presumably this question, the right-hand side of the equation, is simpler than this question, the left-hand side of the equation. So how are we going to actually use this thing? Well, if you stare at this, you might notice that we're going to change one integral, one question, into another question. So you're going to be using this in a situation where you're asked the integral of a product of two things, kind of like we are up here, x times e to the x. So you're like, okay, one of these will play the role of the u and one of them will play the role of dv, but which is which? Well, if you look at what the answer will end up being, the u and the v are done. There's no integral here. Where the work will still be needed to be done after you apply this formula is right here, the v du. So when you're applying your formula up here, you want to look at the two different terms that are being multiplied together. And you want to ask yourself the question, which of these two things would it be useful to take the derivative of if I still had to take the integral of what I got after I took the derivative of one of these two different things? What I'm saying is if you look at this, you might notice that the derivative of x works out really, really, really nicely, right? It's just 1. So if I were asked this question, I would want to let u be equal to x. If u is x, then du over dx is 1, so du is just 1 dx, or you could just write du equals dx. You don't need this 1 as a placeholder. So if I'm letting u represent this x, and I look at my formula here, my formula gives me the integral of u times dv. If u is the x, then dv must be the e to the x dx, everything that's left over. If I want to use this formula to evaluate this integral, the u is the x, everything else must be the dv in this formula. If dv is e to the x dx, then I can ask you the question, what must v be? Wait, what is v? I don't understand. What are you doing here? Well, remember, this is the derivative of this thing. So I'm just asking you the question, what must be here in the blank, so that when you take the derivative of that thing in the blank, you get e to the x. dv over dx has to be equal to e to the x. What was v? Well, I guess it's e to the x. What you have to do when you're using integration by parts is first choose u, then take the derivative of u, then figure out what dv must be by process of elimination, then figure out the antiderivative of dv to figure out v. So when you're applying this formula, you're taking derivatives and antiderivatives. But when you have these four pieces, you can just apply this formula. The integral of u times dv, the integral of x times e to the x dx, is equal to u times v, x times e to the x, minus the integral of v du, the integral of v, which is e to the x, du, which is just 1 dx. What I'm saying is the answer to this question is the same as the answer to this question, because this equals this per our integration by parts formula. You're like, so this is my final answer? No, this isn't your final answer, because this still involves an integral. It'd be weird if somebody was like, what's the integral of something? And you were like, well, the answer is, and part of your answer involved an integral. We got to get rid of this integral, but this integral is easy to figure out. This one's hard. This one's easy. The integral of e to the x, well, the antiderivative of the e to the x is just e to the x. So my answer would be x e to the x minus e to the x plus c. Don't believe me? We can check this. The way we check our answer is we take the derivative of the answer and make sure that that gets us back up to the question. If I asked you for the derivative of this answer, well, x times e to the x, you'd have to use the product rule. You'd say the derivative of f times g is f prime, which is just 1, times g, which is e to the x, plus g prime, which is e to the x, times f, which is just x. So using the product rule, the derivative of this first term is this guy. Using the fact that the derivative of e to the x is just e to the x, the derivative of the second term is just e to the x, and then the derivative of a constant is 0. If I clean this up a little bit, I got e to the x plus x e to the x minus e to the x minus e to the x. I'm left with just x e to the x. That checks. That's what I was asked for the antiderivative of to begin with. That's integration by parts. It's a little bit different. It might be a little overwhelming the first time you see it, but let me talk you through what you actually need out of this video. None of this. I think it's great to understand it. If you can derive formulas, that'll benefit you in future math classes. But for our math class, you need this formula. You need to memorize this formula. And I'm going to say it again. The integral of u dv equals uv minus the integral of v du. If you say this 10 times, you'll have it memorized over again. You need this formula, and then you need to know how to apply this formula. When to apply this formula? In this section, it's easy. It's the integration by parts formula. When to apply it is in every single damn question, right? Because the question is going to involve this integration by parts formula. Otherwise, the question wouldn't be in this integration by parts section. But more generally speaking, when you're asked for the antiderivative of a product of two different things, there's a good chance you'll be using your integration by parts formula. And the way you'll use your integration by parts formula is you'll stare at those two different things, the two different factors that you're multiplying together in that product, and you'll ask yourself the question, how could I make this integral easier? And the only tool I have available at my disposal is to take the derivative of one of those two parts. So in this question, you'd look at this and you'd be like, well, the derivative of e to the x, that's no easier. That's just e to the x. That won't help me. But the derivative of x, that'll make this problem way easier. Why don't I try letting my u be equal to x? Once you know what u is, that by process of elimination gives you dv. Once you know u and dv, you can figure out du and v by taking derivatives and antiderivatives respectively. And once you have these four different parts, it's just a matter of writing them down into your formula. And what that will give you is a new integral. And the hope is that new integral is something that you can evaluate. And if you can't evaluate this new integral, well, then you're kind of back to the drawing board. Maybe you chose u and dv wrong. Maybe you can evaluate this integral, but it needs you to use the integration by parts formula again. Maybe you can evaluate this integral, but you need to use u substitutions. Right? Again, what you'll see is it's not always obvious how to solve these. It's not an algorithm. It's a puzzle that you need to figure out. You're playing with the different pieces, and you kind of hope that choosing this u to be equal to x will make this easier. But you don't know for sure that'll work. is a puzzle. Make your best guess, try it out, see where that takes you, see if you can get closer to the answer, and if you can, great. And if not, you're back to the drawing board and you try another method to solve this problem. That's our introduction to integration by parts. I'll do a whole bunch more examples so we can get some repetition with this stuff, and then I'll show you some advanced methods.